Yes, class. Alia, Austin, Rabah, Humam, Shahid. Am I audible to all of you?
Yes, ma'am.
All right. So in the last class, we had completed till this question, but yesterday I couldn't tell you the directions, right? Let us just quickly repeat the directions. One was this. Yes, this question I wanted to tell all of you. See, if something is going inside, this is kept in, just a second, give me a second. Look here. This plane is known as, this is your regular XY plane. Fine, this is your XY plane. Y-axis, this is your X-axis. So in XY plane. If it is kept like this, now this is your Y-axis and this is your Z-axis. So if the circle of the ring, this is kept like this is what is meant by Z-axis. That is this second one. This. First one is this, XY plane, YZ plane. And if it is kept like this is your X-axis and here it is your Z-axis, ZY plane. So when I have kept it like this, the first string was like this, second is kept like this. This means this is kept in YZ plane. Now the current form, if you look here, if you keep it parallel, current is going inside, right? Then coming outwards. If you look it from outside like this, if you look, current is moving inwards, it is going inwards. So if I curl the right, this is my right hand, if I curl my fingers along the direction of current is going inwards. So my fingers are also, this is the direction of current. So thumb is pointing leftwards, which we discussed. Now is this clear? Yesterday this couldn't be shown. All those who were having doubt. And one more question. See, for circular ring, this is the center. But if we keep it like this, this is the axis which I was talking about. So at its axis, if you want to calculate, this is how you will find it. Lastly, there was one question. Yes, this question. So direction for this question also. Now see the first string is kept in YZ plane and the second ring is kept in XZ plane, right? This is your regular Y plane, but the ring is not kept like this. So how will you get the directions over here? See, if this is kept like this, current is moving inwards, coming out. Current is going inwards, coming out from the bottom. This is what is written on the screen, or this is how the diagram is being placed. Current is going inwards, coming out. So curl, this is my right hand. So I'll curl the fingers along the sense of current. So current moves leftwards for the first one. Fine. Now for the second one, see, this is the second. This is kept like this. Now how the current is moving? See, current is going first towards the right, then from backward towards the left, towards the right, towards the left. This is the direction of current. So I have to curl my fingers along the direction of current. Current is moving like this. So thumb is going upwards. That's why J cap we mentioned. There we had minus I cap and here we have J cap. Now clear to all of you. This was the direction which couldn't be explained yesterday. We just discussed this also. This was left. I told you today, I'll explain you. This is how you have to find out the directions in different planes are kept. Suppose this is the ring. This is moving like this. So curl your fingers like this. If it is moving like this, anti-clockwise, so curl it anti-clockwise. Here, if the current is going inwards, if the current is coming outwards, this. If the current is moving in this manner, from right to left. If it is moving from left to right, like this. In everywhere, you'll have the thumb, which will give you the direction. Now, today we will discuss second thing, that is Ampere's circuital law. This is also very important. See, Ampere's circuital law, but it is easy. See, some of the things you will find it similar to your Gauss theorem, some of the things. But see, from Ampere circuital law, you do have similarity with Gauss theorem, but exactly it isn't similar. Like Gauss theorem, proper statement of Gauss law. Who remembers Gauss theorem? Proper statement of Gauss theorem. Yes, what was Gauss law?
Total flux coming out is Q by epsilon naught.
Q by epsilon. Very good, Shavis. Right. See here what we see. Suppose this is a current carrying wire, which is carrying the current I. Let's say I have marked a loop over here. I have just marked a random loop over here. So some magnetic field will be existing over here. This will be having current element DL, all the things similar to Biot-Savart's law. If I take B dot DL, an integration of B dot DL. So this we call, the way it was in Gauss theorem, E dot ds, electric field dot the surface area E dot ds. So here this is B dot DL, right? B is the magnetic field, DL is the current element, B dot DL. All right. This is current is flowing in the wire. This is the wire in which the current is flowing. I have chosen a loop around it, just a loop around it like this. Like this, you can see I have just taken a loop around it. Now from this, I am taking a very small section, which I am marking it as DL. Now, if I take the dot product, B dot DL, if I take their dot product, so see, this is equal to, so we call this term, which is left hand side, this we call as the line integral of magnetic field. Why line integral of magnetic field? See, this is the loop that we have chosen. This is the current that is flowing, but we are talking about the small section. So, and we are integrating it throughout, how to find out the entire magnetic field. So B dot DL is line integral of magnetic field. All right, in a small segment DL, how much magnetic field is being contained, and we are integrating it to find out the current, to find out the through the entire wire. So line integral of magnetic field, B dot DL, integral of B dot DL. This is equal to, according to your Ampere circuit law, in Gauss theorem, what was Gauss theorem? See, E dot ds closed loop integral is equal to 1 by epsilon naught times. So here we'll have, my voice is lagging. Others, are you able to hear, or is it lagging? It's fine or not, other students, apart from Chavez?
It's fine, ma'am.
It's fine. Okay, see, Chavez, I am saying if you are having, suppose this is a wire which is carrying current. I have chosen a random loop around it like this. Now you can see through this loop, such a small portion is being enclosed, right? A very small portion is being enclosed. So I have taken a very small portion DL, which we call as the current element. Now see, B dot DL, integral of B dot DL means line integral of magnetic field. Means for a small area, for this small length, small current element, we know what is the magnetic field. We are trying to find it for the entire wire. That's why we are integrating it. So integral of B dot DL, that is what we call as line integral of magnetic field. The way in Gauss theorem, E dot ds was equal to 1 by epsilon naught times the charge enclosed. Here in Ampere circuital law, integral of B dot DL, instead of 1 by epsilon naught, you have here direct mu naught. Here you had 1 over permittivity. This is directly permeability. Fine. So integral of B dot DL is equal to mu naught times. Here what you have? Charge enclosed. Here you have current enclosed. So this is your Ampere circuital law. This is your Gauss theorem. Right, so B dot DL, integral of B dot DL is equal to mu naught times the current enclosed by the loop. Current enclosed, now again, same thing as Gauss theorem. Remember when we were discussing Gauss theorem, that time we discussed, if you have a small section, And out of the section, if charge is present, then you won't consider those charges which are present outside the Gaussian surface. Similarly, here also we will draw an Amperian loop. The way we had Gaussian loop, we'll draw an Amperian loop. Now that Amperian loop, out of which if any current is flowing, that you won't consider. All right, for example, see, this is the law. According to Ampere's circuital law, the line integral of magnetic field along a closed loop is mu naught times the total current I enclosed by the loop. So this means if this is what is given to you and you want to find out what is B dot dl, so integral of B dot dl will be equal to mu naught times. Now what is the I enclosed? This is I1 and I2 are moving in the same direction outwards. This is going inwards. So I1 plus I2 minus I3. This is also going outward. So this should also be plus I4. But since this is out of our Amperian loop, we will not be considering it. Now regarding how to construct Amperian loop, we'll study just after this segment. First, you note it down. Yes, Chavez.
And this is like an imaginary loop.
This is an imaginary loop. This is an imaginary hypothetical loop just for our calculations, just to confine the current that is moving. And in your questions also, you will draw it by yourself because since it's an imaginary loop, it's hypothetical. It won't be mentioned anywhere. We just draw it for our convenience because we have to know what is the current enclosed. So we have to draw the boundaries. That's why we consider it. This is not a real loop which is present. Note down these points. Then let us see what is exactly Amperian loop. There are certain properties also, how to choose Amperian loop. You cannot just randomly make Amperian loop. There are certain conditions noted down, then I'll tell you.
Nothing so.
Done till here?
Yes.
Now let us talk about the Amperian loop. So first condition regarding an Amperian loop is that it should be closed. Secondly, magnetic field should either be tangential or perpendicular to it. Means if you are constructing an Amperian loop, magnetic field should either fall tangential or perpendicular. So in the questions also, in the numericals also, usually the magnetic field is going inside or outward. So that is also making this as perpendicular. Then it says that magnetic field should be uniform throughout. It means value of magnetic field has to be constant. If you're choosing a variable magnetic field, then your Amperian loop is not valid. And if your Amperian loop is not valid, then entire Ampere's circuital law, this is not valid. All right. Now, certain steps regarding how to choose an Amperian loop. See, for the basics, for the very basics of your Ampere circuital law, see, magnetic field, firstly, it has to be uniform. Now, suppose we have chosen an Amperian loop, a random Amperian loop we have chosen. Expand the second point, tangential and perpendicular. This one, see, magnetic field should fall tangentially or perpendicularly. For example, this is Amperian loop and magnetic field is going inwards. Usually in your syllabus, in most of the questions, magnetic field is present inwards and outwards only. So suppose magnetic field is going inwards. So inwards will be like this, right? Now look here. It is actually perpendicular to the Amperian loop. Similarly, if it is going outwards, then you can see here also this is perpendicular to it. So even if it is tangential or it has to be perpendicular like this. This is the line of forces for magnetic field or this way, like parallel to the diameter or perpendicular to diameter like this. This is what is meant by magnetic field should either be tangential or perpendicular. Fine. Now coming to these steps. Ampere circuital law, suppose this is a wire and through the wire we have chosen an Amperian's loop, radius is r. Now B dot dl is equal to mu naught I enclosed. This is the rule. This is the actual rule which has to be abided. Why? Because Ampere's circuital law statement is this only. When you go by the statement of Ampere's circuital law, the statement of this is only that of Ampere's circuital law is that line integral of magnetic field is actually mu naught I enclosed. So we'll be starting from here only. Now see, B dot dl if we solve it separately and I enclosed if we solve that separately. All right. Now B dot dl, this becomes B dl cos theta. Look here, magnetic field and length. We have already discussed that the condition is that this has to be, so we are already assuming over here that magnetic field, this is perpendicular or tangential to it. Because as the question will come through that, it will become more clear. So as to what is exactly given. Now see B dot B dl cos theta will be written. Now here cos 0 degree will become, because magnetic field and dl right now we are considering this is the magnetic field. If it is perpendicular to Amperian loop, it means it is going through here only, that is parallel to the length, then only it will be either tangential or perpendicular. So this usually this will become B dl only, B integral of dl. So if you are integrating this, and we already know that magnetic field is constant. So when something is constant in your integration, magnetic field will come out because this is a constant term. This is exactly what we are following the conditions. So it means B integral of dl. When you are taking dl, do not calculate the entire surface area of the wire. No, when you have considered Amperian's loop for Ampere circuital law, then everything will be from that Amperian loop only, from that Amperian's loop only. I will not consider the entire, suppose this is the wire. So I won't consider all the length of this wire. All right, I won't be consider this entire length of this wire. If I'm taking integral of integral of dl, where magnetic field is already constant. So it means dl for this Amperian loop, that is 2 pi r only. So this becomes B into 2 pi r. Now let's say the current is I. I enclosed one. This type of question is here. So properly in the form of question we will do, but the basic steps you all should know is I. So it means we can write B into 2 pi R is equal to mu naught I. Ultimately, we have to find out magnetic field in every question. So that becomes mu naught I by 2 pi R. So this is the basic method how to solve Amperian circuital law or form Amperian loop, find out the value of magnetic field. But a proper question, this has come in your JE exam. This has once come in your NEET also. And in your CB also, CBSE, it's a previous year question that we are going to discuss. But before that, note down all these points, then we will discuss. It is totally based upon the application of Ampere's loop. In fact, if it is possible, try to remember that formula. That I'll tell you once we start with the question. First, note down all these Amperian loop, all the points. See, class, for this question, no, a long cylindrical wire of radius A has current I flowing. You have to find out the magnetic field inside the region in the wire. See, it's a narrow region is being drawn. So consider an Amperian loop of radius R. The radius of cylinder is A. So the outer one is your cylinder, the light blue one. This is your actual wire. And we are taking a very small Amperian loop over here. Now class, the problem that arises now here is answer would have been directly integral of B dot dl is equal to mu naught I enclosed simply. But problem is with I enclosed. Class, through that entire wire current I is flowing. And here we are taking a very narrow portion of it. That is a smaller Amperian loop we have taken. Current I is through the entire wire, not with just this small section. That's why we cannot consider I. Here is the problem that arises. Otherwise, our answer would have been in one line only, the way you have written right now in your notes. So, see, current through pi A square. If I talk about this entire area of this sky blue one, the outer actual wires area. This is the Amperian loops. This is the wire. So if I tell you what is the current through this pi A square, means this area, that is I, not through this. We need to find out what is our I enclosed. That's how, and this is a very, very, very important question, very important. For all of your entrances, for all of your CBSE questions from Amperian loop, this question, you have to at least revise it once every time whenever you are revising this lesson. So current enclosed through pi A square. This is I. So what is the current enclosed through one unit area? Current enclosed per unit area. That will become I divided by pi A square. Now, if you know what is the current per unit area, for one unit area, if you know what is the current, can you not find out the current for pi R square area? For just this part, you can. Current through pi R square will be I by pi A square multiplied to pi R square. Pi gets cancelled. Now you actually have the value of I enclosed with you. I enclosed, it is not I this time. It is I R square divided by A square. This is the actual value of your current enclosed for this, because entire was, suppose this was the wire and our Amperian loop is located within just this part, right? So it means for this part we are finding out, not the entire wire. This is it. Now you have I enclosed. Now rest of it is similar. Integral of B dot dl is equal to mu naught I enclosed. B is a constant. Integral of dl is equal to mu naught I enclosed is what? I R square divided by A square. Integral of dl. What is the integration of this dl? dl is from the Amperian loop. So for the entire Amperian loop circle, do not get confused through the wire or through the Amperian loop. Always it is through Amperian loop only. Everything is with reference to Amperian loop only. So integral, this will become 2 pi r, not 2 pi a, is equal to mu naught I R square by A square. This square cancels this R. Finally, you have the value of magnetic field as mu naught I R divided by 2 pi A square. This value, please remember it, class, because there are many graphs which are given based upon this. Learn it as it is. Suppose this is given, this is what it is given. In the following region, magnetic field is inside the wire. Suppose it is given outside. Now for outside, it is very simple. Suppose this is your wire. An Amperian loop will be outside. Now small r will be greater than your A. This will be greater. This would be the case. Now your B through pi r will directly be equal to mu naught I, because now the current I that is flowing, this is already enclosed. So you don't need to find it for this section because your I is already getting enclosed. So for inside, your formula will become mu naught I by 2 pi r. This is, both of these are very important. This is for outside. This is for outside. Earlier we did it for inside. Once more, we will see this. Once more, we'll see this because the graph is also very important. The formula is also very important. Before coming to solenoid and toroid, write down the solution for this question. From Amperian loop, from here, no? From of this question or the actual heading of Amperian loop? This part only, Chavez? Heading, acha. Heading, this.
Yes, sir.
This part, Chavez? Which part?
Down.
This?
No, more down.
This one?
Yes. You can scroll more. I mean down.
Written all this?
Yes.
Okay.
Okay, scroll up. Yes, I'm done.
Completed till here? See, now under the applications of Ampere circuital law, you have two devices. One is called as the solenoid, second is known as the toroid. So understand solenoid in detail, you will be able to understand toroid also. Basically, solenoid is what? Solenoid is just turnings of wire, insulated wires which are present, copper turnings of the insulated wire like this. If you take a wire and you are wounding it, that is what is meant by a solenoid. But now for our calculation purpose, we will consider a portion of solenoid. Let's say this one part. See here, This is one section. You are seeing it from the transverse part. If this is the solenoid, no, if the entire, this is the solenoid. If I cut it this way, this is what is known as transversely. So this is a transverse section of the solenoid. See, if it was in the ring form, current was coming out, from here it was going in. Then from here coming out, going in, coming out, going in. That is through the entire solenoid. So this is what I have shown also by drawing this. All this is current that is coming outwards, going inside, outwards, inside, outwards, inside. Like this is what we have shown. If you cut it, you will be able to see one part. From here current is going in, from here current is coming out. So that is what we have drawn. So here also we'll consider an Amperian loop for our calculations. Let's consider a portion outside also. And from here, let us consider this inside also. This is A, this is B, this is C, this is D. So this is the Amperian loop ABCD which I have taken. All right. Now see, for all the parts we have to find out. So again, I'll tell you this part, this means current is outwards.
Yeah, ma'am.
And this means current is inwards. So it's like this, current is going in, coming out, going in, coming out, going in, coming out. Because it is difficult, no, for all of us to learn it on this. This is the actual. If you cut it from here, you will see current going in one turn, coming out, going like this, it will keep on moving. Now, through this, how we'll find out now our answer. So if this is our Amperian loop, we know what is B integral of B dot dl is actually equal to mu naught I. So for the net B dot dl, we cannot have only one side. We have to take line integral of B dot dl from A to B first, plus then line integral of B dot dl from B to C. Then line integral of B dot dl from A to B, B to C, C to D, plus lastly from D to A. This is how we'll get it. Now see, for all of this, we have cos theta. So coming to AB, look here. This is your wire AB, right? Now, only if you look here, this part, AD and CB, these two, this segment is only making an angle of 90 degrees, right? If you look here, this isn't making an angle. This is directly parallel to the wire of solenoid. This is perpendicular to the wire of solenoid. So for these two, we'll have 90 degrees. For these two, we'll have 0 degree, right? So if we are talking about A to B, from A to B, if we are talking, then cos 0 degree will be used. But as you can see, B to C, this is perpendicular to the wire. Yes?
How it is perpendicular?
Yes, Chavez, what are you saying?
How it is perpendicular?
Can you type, Chavez? Your voice is coming very low. Please just type. This is perpendicular, not to the wire. See, this is the wire, the entire solenoid, right? That's why we have taken a transverse section. I have taken a rectangular loop from here. A loop I have taken in such a way that some portion is outside. Why outside? Because then it would be unfair. We do not know what is the current if it was taken outside. So we have taken it in such a way that some part is enclosed also, some part is outside also. Now, if you look this CB, this is making 90 degrees. I have not drawn it very straight. It is actually a square. So if you draw a square over this wire, so this will be 90 degree only. This becomes parallel, this side becomes parallel, this will be again 90 degree. That's why only these two are making an angle of 90 degree. These two are making an angle of 0 degree. So if you write it, this becomes cos 0 degree plus B to C, this becomes BDL cos 90 degree plus C to D, this becomes BDL cos 0 degree plus this becomes BDL cos 90 degree. Now look, BDL cos 0 degree means integral. This is actually integral. This means integral of BDL. Fine. Cos 0 degree, this becomes 90 degree. Again, this becomes B integral of DL plus this cos 90. So these two are directly 0. But one more thing, class. One more thing. For the segment CD, how much magnetic field is actually there? Just this segment CD. Do you see any magnetic field actually getting enclosed over there? Do you think any magnetic field is actually present in the segment CD? CD, I have taken it in such a manner that we are getting some portion outside and magnetic field is running. This magnetic field that I have drawn, these dots, these are within the wires only. And since no wire is here, through this section also, there isn't any magnetic field. Though angle was 0 degree, angle is still 0 degree, which is parallel to the wire. This is 0 degree. But there isn't any magnetic field. If in the equation BDL, B is 0. So BDL will have any value? No, BDL will also be 0. So only AB, this segment has magnetic field also. You can see we have enclosed a portion of magnetic field. These are already perpendicular to it. And this was parallel. But this is outside. So no magnetic field is actually enclosed within this portion. So finally, from this region also you have B. L is the length of the, let's assume length of the side is L. B plus 0. This also becomes 0 and this was already 0. So finally what we are left with BL, and L is what? L is length of side AB. The total length, because we do not know what is the length of the segment. I have always told you in the previous part also, when we are taking a circle, that always consider the Amperian loop only. I'll not take the length of the solenoid. I'll take the length of the Amperian loop. The way in the previous part for the circle, I didn't take 2 pi A. A was the radius of the circle. 2 pi R. R was the radius of Amperian loop. So let us assume L is the length of this AB. So BL we have on one side. Now see, coming to number of turns, this was for one portion only. If number of turns per unit length are small n, so for L length, for one turn, for 1 unit length, we have n number of turn for 1 unit length. So for this L length, AB, what will be the total length? N into L. So now let us equate the right hand side with the left hand side. Left hand side is now BL only. B dot DL, entire thing we have integrated, line integral has ultimately come out to be BL. Rest of the things became 0. 2 were 0 because cos 90 degree was 0 and 1 was 0 because no magnetic field was there. So since magnetic field is only not present, why would we have it? And mu naught, what is the current through the length? This becomes NLI. This is the I enclosed, no, right now. So length gets cancelled. You finally have the formula B is equal to mu naught Ni, where N is what? N is the number of turns per unit length. Here small n is number of turns per unit length. All right. Suppose this is not a long solenoid. Long solenoid means ends are extending up to infinity. Suppose this is not a long solenoid, not a long solenoid. So if at the ends you want to find out the magnetic field, that derivation is not in your course. Directly remember the formula mu B is equal to mu naught Ni divided by 2. That it would become for the ends. If you are talking about ends, but usually you have long solenoid in your syllabus. Whenever you see the term long solenoid directly means, see, if you have this long solenoid, solenoid means infinite. And yes, I was saying number of turns. See, number of turns per unit length, it would become, suppose number of turns are n in the wire, per unit length will become n. So depending upon the question, you have to write it. Also, you have mu naught over here. Mu naught we have discussed, this is permeability only for air, right? 4 pi into 10 to the power minus 7 is particularly only for air, this value. That's why we put a naught. Suppose you have a different formula, you have a different medium, the solenoid is kept in a different media, right? In that case, what will you do? Same thing, what you have been applying in your Biot-Savart's law. Multiply it with mu r. That's it. Mu naught into mu r ni. That becomes your formula. Question, before the question, write down the derivation. From here, yes, application. So toroid is easier as compared to solenoid. Derivations are based on this only. You have to take region wise only. You have to solve an Ampere circuital. Note it down. This derivation comes in your syllabus, comes in your exam. So do not ignore this. This derivation is also important. Ampere circuital law is completely important. All the laws, no, Biot-Savart's law, Ampere circuital law, these are very important.
Again, scroll up. Enough, enough.
Figure are you asking?
Yes, I'm there.
Text me done once you have written it till here. Fine, all those who have completed, you can leave. In the next weekend, we'll complete with this also.
Thank you.